next lesson, the next theory part in this lesson is speed of longitudinal waves along rods. Now, we discussed about stretch strings. Even in stretch strings, we can create longitudinal waves, but normally we use longitudinal waves concept for rods. Now, when you, let's say you have a rod or a stretch string, now rods are rigid. Okay, imagine now this is a rod. If you fix it like this, it will stay this way. But if it's a string, if you fix it like this side it will fall down, this side also it will fall down, because strings are not as rigid as rods. So rods are different. You can clamp rod with just one support, a rod can stay. Okay, even if I hold it like this, see the rod if it's a rod, it's rigid. But if it's a string, if I fix it here, what will happen? It will just fall down like this. It won't stay. That's the issue with strings. So normally this concept is considered for rods. If you want to create longitudinal waves, we have learned that longitudinal waves travel parallel to the direction of propagation. I mean, longitudinal wave means the particles oscillate parallel to the direction of propagation of wave. So you need to vibrate this what do you call that, rod in this direction, in this way. This is how you need to vibrate the rod. Okay, not this way. If the rod vibrates this way, it will become transverse. So you need to find a way to oscillate the rod this way. So you can create longitudinal waves. Just like the speed of transverse wave, I hope you can remember speed of transverse wave is equal to square root of T over m, tension and mass per unit length. We just discussed that equation. We just did not derive that equation. Likewise, here also there is an equation. We don't derive it. So let me write that. Well, this is that equation. Okay, V equal again a square root y over rho. If not, sometimes they will use capital E over rho. You can use any equation you prefer, but it depends. In several teachers, different teachers teach in different ways. I normally prefer this y over rho. Whatever it's convenient to, you can use it. Now, V is the speed of longitudinal wave, that's not a problem. Rho is the density, you can see rho, and Y is called Young modulus, if not elastic modulus. Now, iron has a particular density, zinc has a particular density, aluminium, copper, they have particular density. So, that density is a property which depends on the nature of the metal. Likewise, Young modulus also depends on the nature of the metal. Now, aluminium will have a particular Young modulus value, copper will have a particular Young modulus value. Okay, so for speed of longitudinal wave, we know it is going to be meters per second, and for density we already know it is kilograms per meter minus 3, and for Young modulus the unit is Newton meter minus 2, or they might use Pascal also. Okay, right, that is Young modulus. But I know you are a bit confused about Young modulus. We will be learning about Young modulus in grade 13 third term under a lesson called properties of matter, elasticity. Under that only we will be introducing Young modulus. But in units and dimensions, I think we have learnt about Young modulus, because Young's modulus has the same unit and dimensions of pressure. Now, I will quickly give a small explanation about what this Young modulus is. Now, imagine there is this rod or even a string, it's fine, right? You give a force. In Hooke's law we learned, you apply a force. When you apply a force, what's going to happen? Its length is going to increase a little. Its length is going to increase a little due to the influence of that force, and the increased length I will take it as delta x or delta L, whatever. Okay, delta x, we took it as delta x in Hooke's law also, delta x. And let's take the cross sectional area of this what do you call that, rod, as capital A. Okay, and also just like Hooke's law, we need the initial length. So I will mark the initial length here. I hope you can understand. Initial length I will take it as L naught. L naught. L naught is the initial length of the rod. Delta x is the extension. Delta x will not be very large like this. It will be just millimeters. But for our convenience, I have drawn it like this. Now, what is this Young modulus? The equation which connects all these components. There are 4. The force applied, the tensile force applied, the cross-sectional area of the rod, the initial length of the rod, the extension in the rod. Okay, all these 4 are connected by one single equation, and that equation is given by this. Force over area equals to Young modulus into delta x over L naught. This is that equation. Okay, I am repeating this, we will learn in grade 13, don't worry. Okay. Now for F over A, we normally learnt it as pressure, but in that lesson we normally have another word, we call it stress. And this one, the extension divided by length divided by length, we call it strain. So if you want a proper definition for Young modulus, you can say Young modulus is equal to stress divided by strain. Correct? When I say strain, it's the whole fraction, not just L naught. L naught is the initial length, delta x is the extension. So I have defined those components, careful. This fraction is only strain, this fraction is only stress. So that is what Young modulus is. By the looks of it, you will be able to figure out that Young modulus has the dimension of pressure, that is ml minus 1 t minus 2. Why is that? Why is that? Now look at this. Strain is extension over initial length, length divided by length. When you divide length by length, it will not have any dimensions. Here we have force over area. When you say force over area, it is the dimension of that is similar to pressure. So the dimension of y and dimension of F over area must be same, because this does not have dimension. So the dimension of y is this. Okay, this is why I took all this time to figure this out, the dimension of Young modulus, because we have, without proving, we have just introduced an equation. So we have to make sure that the equation is dimensionally accurate. How do we do that? We consider left hand side dimension and right hand side dimension. Let me quickly do that. So when you consider the left hand side dimension of this equation, that is the dimension of speed. What is the dimension of speed? Lt minus 1. Okay. Then when you take the right hand side dimensions, we have the dimensions of square root of y over rho. Okay. So the dimensions are going to be square root of the dimension of Young modulus, it's the dimension of pressure, so it is ml minus 1 t minus 2 divided by dimension of density, mass per volume, so that is ml minus 3. Okay, ml minus 3. So we know these letters m and m will get cancelled off, and finally we will get square root of L square t minus 2. How is that? We already have L minus 1. When this L minus 3 goes up, it becomes L cube. So L square this, and finally the right hand side dimensions are also Lt minus 1. So left hand side dimensions are equal to right hand side dimensions, hence this equation is dimensionally accurate. Just like the transverse wave, speed of transverse wave equation, you just have to derive this. Okay. As far as I know, as far as the syllabus is concerned, knowing this equation is more than enough for you, because we don't normally dig deep about the longitudinal waves created in rods, but I will give you a small explanation about the types of longitudinal waves which can be created on rods. Now rods can be clamped or fixed in three different ways. What are those waves? Sorry, what are those ways? The first way is this: you can clamp a rod or fix a rod like this. You fix to two ends. Okay, this is a rod, you have fixed it, and you are creating vibrations like this. Then it will be the way the vibrations created are similar to the vibrations created in the stretch string. Now this part is might be a little confusing to you. Here also we draw the wave patterns like this. We draw the wave patterns like this. We do, even though the particles vibrate in this direction, or even the particles vibrate in this direction, it's very difficult to draw the waves, right? How are we going to draw it? In this direction there's nothing. It's like we will not see anything because it's happening inside the rod. So for anyway, it will happen similar to the standing wave in stretch strings when they are plucked perpendicular. That means the middle part will oscillate more, but this part and this part will not oscillate at all, and part here will oscillate less. So that we draw like this, the standing wave. What is the meaning of this wave? This wave, we are talking about longitudinal standing waves, right? Longitudinal standing waves. When I draw a longitudinal standing wave like this, it doesn't mean the particles oscillating like this. It's actually this particle is oscillating at a high amplitude. This particle is oscillating at lower amplitude like this. this particle and this particle are not oscillating at all. Now this is the same type of wave patterns, we have already discussed it 3-4 times, so we don't have to repeat it. Let's forget about this. This is the first case, how you can fix a rod. The second case, the way you can fix a rod is this. You can fix a rod like this. See if you can agree with me on that. Yeah, because you can fix a rod like that. See, it stays. If you fix, I fixed it here, it stays this way. Okay, it stays this way actually. And when you create oscillations, the waves can be formed in different ways. Now the fundamental wave here, I'll draw it a little down here. It's going to look like this. See if you can agree with me. This is the wave. Okay, at the free end we should have antinode. At the fixed end we should always have node. This is the first fundamental wave and the fundamental mode. And then the first overtone, it's going to look like this. Why is that? Always antinode at the free end, always node at the fixed end. Okay, the number of loops we have somehow increased. This is how the loops will increase. This must be half of this. That's how you have to draw. Then the last one, not the last one, the third one, I'll stop after 3 like this. Okay, that is how it is. These are the standing waveform. This is, I don't think this is very necessary for you. I'm just explaining it a little additional. I'm explaining a little additional information. Let's say the length of this rod is L. Okay, right. Now we are going to compare the wavelengths. Now here, this is half of a loop, correct? So here, wavelength, I will take it as lambda naught. Lambda naught by 4 is only going to be equal to L. I will stop there. You can after this you can continue your questions if they ask in case. Now here we have one loop and half a loop. So this one is actually 3 lambda 1 by 4, correct? 3 lambda 1 by 4 equals to L here. And if you take this one, it's going to be 2 loops, so that is lambda, and another half loop, that is lambda by 4, altogether 5 lambda 2 by 4 equal to L. Okay, 5 lambda 2 by 4. That's how this it's going to look like. If the rod is clamped and in the corner, and when you make standing waves created in the rod. Okay, fine. That is how it is. And then the third way you can form waves on a rod is you can take a rod like this, and you can clamp it at the center like this, exactly at the center. What is that? This. See, it stays. And there the waves will be formed. How are the waves going to be formed? The standing waves. At the fixed points always nodes, at the free ends always antinodes. So the first one, it's going to look like this. Okay, and the second one always node here. So the second wave pattern will look like this. This is how it's going to look like. Yeah, why is that? Node at the center always, antinodes at the corner. And the other one, the next one, it's going to be this. In case if you get questions, this is how you have to handle them. Remember, this is little different from what we learned earlier. This is how the standing waves are going to be formed on the rods. Not only longitudinal, even transverse can be formed like this. Transverse waves, when you vibrate a rod like this, you can consider like this. Okay, right. Now here, when you take the lens, what about this one? Quarter loop, when you consider both, it's half a loop. So there again, lambda naught by 2 is actually L, if you take the length of this as L. Here we have half loop, complete loop, 2 half loops, altogether 3 loops, means 3 lambda 1 by 2 equals L. Here we have 1, 2, 3, 4, 4 and a half, 5 loops, that means 5 lambda 2 by 2 equal to L. There it was lambda naught by 4, 3 lambda 1 by 4, 5 lambda 2 by 4. Here it is lambda by 2, 3 lambda by 2, 5 lambda by 2, something like that. Okay, so in case if they give you rods clamped at different places, this is how you compare the wavelengths. I hope you understood that. And this equation you have to know. You don't have to know how to derive it, and I have given you a small explanation about Young modulus. For the time being, this is enough. Later in grade 13 we will study about this deeper.